You must have seen this picture in the context of the Heisenberg's Uncertainty Principle in quantum mechanics, which says that if the spread in position is small, then the spread in momentum will be large, and vice versa. But the interesting thing is, you can also see this correlation in the context of waves in classical physics. In this video, we'll find out where the similarity comes from and where the difference really lies. To understand why the spread of a wave in one domain controls the spread in another domain, we need to first understand Fourier transform. If you have a time domain signal, then using Fourier transform, we can see the signal in the frequency domain. So Fourier transform is a transformation from time domain to frequency domain. Suppose you have a finite series of a harmonic signal. If you do the Fourier transform of this signal, then you will get a single spike at the particular frequency. Suppose we have another signal. Now, by seeing the time domain signal, we cannot specifically say whether it is a single frequency or two frequency or whether there is noise in the signal. Now, if we do the Fourier transform, then from the Fourier transform, we can see that this signal does not have noise and it contains two frequency, F1 and F2. This is another example. Here on the left hand side, we have a time domain signal. And when I'm doing the Fourier transform, I can see that there is one dominating frequency F1 and there are some noise in the signal. So far, we have used the Fourier transform to go from time domain to frequency domain. And the frequency here, it is called the temporal frequency. That is number of cycles of a wave passing a fixed point per unit time. But Fourier transform are not limited to time. We can use them in space as well and transform to different type of frequency. For example, we can transform to the spatial frequency, and this is defined as the number of cycles of wave fitting per unit distance in space, and the relation is given by 1 by lambda. We can even transform to angular spatial frequency, which is defined as the rate at which the phase of a wave changes per unit distance, and this is given by 2 pi by lambda, and this is what the physicists call the wave number. So Fourier transform can also happen from position domain to angular spatial domain, and that is what we are going to focus on. Now let us look some of the examples of Fourier transform from position space to k-space, that is the wave vector space. If you have a short pulse, and then in the k-space it will be a broad spectrum. If you have a partially spread wave group, then in the k-space you will have a narrow but finite spread. What about the Fourier transform of a Gaussian profile? Now, the Fourier transform of this profile will also be a Gaussian profile, but with some slight changes in the width. That means Fourier transform of a Gaussian function is also a Gaussian function. This is very important because it is the key in finding the minimum possible value of the product of the spread in x and the spread in k. Now, let us see what happens to the spread when we do the Fourier transform. In this example, I have taken the spread in position to be small, and when we do the Fourier transform, we can see that the spread in the wave number is large. And in the second example, we can see that the spread in the position is large, but the corresponding Fourier transform, the spread in the wave number is small. So from these two examples, we can say that if a function is localized tightly in the position space, its Fourier transform must be spread out in the wave number and vice versa. Now, this is what we call as the Fourier uncertainty, and mathematically we can represent it like this. Here, delta x is the spread in position and delta k is the spread in wave number, and it is equal to half when we take the Gaussian profile. But if you take other type of shapes like rectangular pulse or wave group, then the product of these two spread is always greater than half. So we represent it like this. So this is the mathematical expression of the Fourier uncertainty principle, and this is due to the wave nature. In quantum mechanics, we can treat a wave like a particle or a particle like a wave. This is known as dual nature in quantum mechanics. Now, in this dual nature, waves are involved. Now, when waves are involved, that means the Fourier uncertainty will be retained. Now, the question is, what's the quantum version of this uncertainty? In quantum mechanics, there is a very important constant known as the Planck constant. Initially, this constant appeared when people tried to fit the Planck's formula on the black body spectrum curve. Later on, Einstein used this constant to propose the idea that electromagnetic waves are packets of energy known as photons. And again, using the experimental data of photoelectric effect, the value of this constant was confirmed. Then later on, de Broglie used this constant value to propose his hypothesis, that is, if there is a particle with a momentum p, then we can associate a wavelength given by this relation. And this was again later confirmed by the Davidson-Germer experiment. So this constant h, known as the Planck constant, it sets the scale where the wave-particle duality becomes significant. Basically, h is this constant, Planck constant, it is the bridge between the k space and the momentum in quantum mechanics. Using the de Broglie's relation, we can express linear momentum in terms of wave vector. And using this relation, we can say that the spread in p will be of the order of the spread in the wave number. Now, we already know that because of the wave nature, the Fourier uncertainty will be retained in the quantum world. So, this delta x into delta k, we can write as delta x into delta p, because k and p, their spread will be of the same order. But it will be greater than or equal to some lower limit. So, what will be this limit? This limit will be the Planck constant. Why? Because Planck constant is the scale where the dual nature becomes significant. Now, if you do the math, then we can find the exact value of this lower limit, and it is equal to h bar by 2. And interestingly, this equal to h bar by 2 comes when the profile, when the wave function, it's a Gaussian function. So, in summary, quantum uncertainty, it's the Fourier uncertainty expressed in the quantum world. Thank you everyone for watching this video.